So practically what I'm going to teach today will not be the part of medicine. So don't worry about that. But it does not mean that you you should not focus, because that will be part of so many other things. Today I'm going to start the third lecture, that is on Airy stress function. Okay, so this is something quite simple and mathematical, and it is not something very difficult also. So I'm going to start. I have started the recording also. So Airy stress function is a function that satisfies the equations of equilibrium. So till now you have studied various types of equations of equilibrium in different kind of coordinate systems, in cylindrical, in spherical, in rectangular. Okay, and equations of equilibrium are basically differential equations. So solution of a differential equation will be a function. Okay, so Airy stress function is something that is basically written as a solution to those differential equations of equilibrium. And Airy stress function is mainly useful in case of planar problems. If you remember, in the last class, we discussed about the planar problem, where we discussed about the plane strain problem, correct? So plane stress problem or plane strain problems can be solved easily using the Airy stress functions. So this is a very important function which can be a good solution approach for plane elasticity problems. So, okay, now unification of plane strain and plane stress problem. So if you remember, in the last class I also discussed that plane strain problem and plane stress problem, both problems are connected by the equilibrium equations, because equilibrium equations are same for both plane stress and plane strain conditions. So it means there can be some connecting, what should I say, link between these two types of problems, plane strain problem and plane strain problem. So that connecting link is very important to know, because Airy stress function is mainly devised to solve these plane elasticity problems. So if you can unify the plane strain problem and plane stress problem, then you can very easily solve all the problems of plane elasticity using Airy stress function in one generalized approach. So here I will give you some very brief idea about how you can unify the first. I will discuss the unification of plane stress and plane strain conditions, and then I will come to the Airy stress function part. So that is nothing complicated, and this is an easy thing. So unification of plane strain and plane stress problem. So one more thing I want to announce. So next semester I have proposed two courses. One is blast engineering and one is uncertainty analysis in civil engineering. So based on your choice, you can fill that form which course you would like to study. Okay. So have you all filled that form?
Yes, sir.
Okay. So because based on that observation only I can decide which course should I float. Otherwise, because I cannot teach two courses. Okay, I have to teach one course, and so the course which will have more number of interest, I will float that course. Okay. So you can ask your other friends, those who are interested in taking these courses, so they can fill their choices. So now coming back to the point, unification of plane strain and plane stress problem. Okay. So in tensor notation, okay, the equilibrium equations can be written as equilibrium equations can be written as sigma ij comma I plus fi equal to 0. You remember? So basically for rectangular coordinates we have written sigma ij comma I plus fi equal to 0. So comma I denotes what? Partial derivative with respect to I, correct? So here, because we are dealing with the plane strain and plane stress problem, so basically we will say I goes from 1 to 2. We will not consider 3 here because we are considering only plane elasticity problem. So there will be only two components, 1, 2, x, y, I, j, okay? And j will go from 1 to 2, not 3, because even if you consider that part will become 0. So basically we are not using that, not 3, because plane elasticity problem. Okay. So let us expand this one. How do we expand? So that will be summation I equal to 1 to 2 sigma ij comma I plus f, sorry, this was j, fj equal to 0. So here you are putting summation on I, not on j, because I is repeating here. So again you can write sigma 1 j comma 1 plus sigma 2 j comma 2 plus fj equal to 0. If you further write, this will become del sigma 1 j del x1 plus del sigma 2 j del x2 plus fj equal to 0. Now for j equal to 1, you can write, if you put j equal to 1, you will write sigma 1 1. So sigma 1 1 is nothing but sigma xx. Del x1 is x plus del sigma 2 1. So 2 is y, 1 is x, and del x2 is basically y plus f1, 1 is basically x. So you can write. Similarly, for j equal to 2, you can write del sigma xy del x plus del sigma y del y plus f y equal to 0. So like that you can write the two equations. Now for the purpose of unification, we will introduce a parameter s. So let introduce a unification parameter denoted by s. So s is basically defined like this: 1 upon 1 minus nu. Nu is your Poisson's ratio for plane strain problems, and s equal to 1 plus nu for plane stress problems. So just keep this somewhere on the side. This is something very important, and how we will use that I will show you. After this, let us write constitutive relations for plane strain. So you please look into your notes and tell me what was the constitutive relation that we wrote for the plane strain problem. Rohit?
Yes, sir.
Please look back into your notes and tell me what was the constitutive relation for plane strain problem. Rohit?
So I am getting sigma x is equal to.
So I wrote a constitutive relation in the last class for plane strain problem using in the vector and matrix format. So can you please tell in that format? So if I tell, it was something like that: sigma xx, sigma yy, sigma xy, right? And then there was something, and here it was something like that: epsilon xx, epsilon yy, and epsilon xy two times.
Yes,
So
sir.
what was
E
here?
upon E
Eh?
upon E upon 1 plus mu
Upon 1 plus mu,
into 1 minus 2 mu.
1 minus 2 nu,
A matrix one first element 1 minus mu,
1 minus mu,
diagonal element 1 minus 2 mu second.
here 1 minus mu.
Yes, sir. Third is 1 minus 2 mu upon 2,
Okay.
and other elements are 0.
0, 0, 0, 0, 0, 0, 0, 0. This one.
Yes, sir. Yes, sir.
Is it correct?
Yes,
Shraddha?
sir.
Some mu was also there.
Where?
Uh, After 1 minus mu, first row, there mu was there. Yes, sir.
So new. Correct? Is this correct, Shraddha?
Yes, sir. Correct.
Okay. So this is the correct relation. So Rohit, you got your mistake.
Yes,
So yeah, you should correct it. So this was the constitutive relation for plane strain. Similarly, it can be shown that constitutive relation for plane stress will be, so again I will write the same stuff: sigma xx, sigma yy, sigma xy equal to, and here I will write the same thing: epsilon xx, epsilon yy, 2 times epsilon xy, and here it will come E upon 1 minus nu square, 1 nu 0, nu 1 0, 0 0 1 minus nu by 2. This becomes for the plane stress problem. The earlier one was for the plane strain problem. Okay. So now here comes the unification part. Unification part. So we can write the two constitutive equations like this: sigma ij equal to 2 mu epsilon ij plus s minus 1 upon 2 minus s epsilon kk delta ij, where I, j, k, all of them, they will go from 1 to 2 because this is a plane problem. So now you can check yourself by expanding this one, that this will give, you have to use the appropriate value of s. Okay, if you use the appropriate value of s, you will get these relations. So if you, for the plane, sorry, for the, I have to insert some blank sheets here, new slide. I think one will be enough. So for, if you talk about the plane stress problem, so that factor was s minus 1 upon 2 minus s. So can someone tell what is the value of s minus 1 upon 2 minus s for the plane stress and for the plane strain? Saurabh?
Hello.
Saurabh, tell me the
Yes,
value
sir.
of stress. S minus 1 upon 2 minus S for plane stress. Because this factor was coming in the combined constitutive equation. So you have to tell that. Thank you. Saurabh?
Yes, sir.
Tell me the value of S minus 1 upon 2 minus S for plane stress situation.
Sir, I think it's 1, sir.
I think it's 1. What do you mean by I think it's 1? You have to put the value of S. What was the value of S for plane stress? Shraddha?
Yes, sir. So mu upon 1 plus mu.
Mu upon
1 plus mu.
1 plus.
1 plus mu.
Are you sure?
Yes, sir.
Minus.
Minus.
Minus new.
Who told this minus?
Sougand.
Sagan, very good. There should be a minus. You are right. Absolutely right.
Yes, sir. Minus.
Okay. So don't make silly mistakes in the midsem because small mistakes can lead to big losses. Now S minus 1 upon 2 minus S for plane strain. Shiva.
Sir,
S minus 1 upon 2 minus S for plane strain.
mu.
Put the value of S for the plane strain case and solve this and tell me.
Yes, sir. 1.
Everyone.
Sir, mu upon 1 minus 2 nu.
Mu upon 1 minus
2 nu.
Very good. This is the correct answer. So basically you got this parameter for plane stress and plane strain, and if you put that parameter in this unified constitutive equation for plane stress and plane strain, accordingly you will get either this one or this one. You will get. So that's how you can, using the parameter S, you can unify the plane elasticity problems, the plane strain and plane stress problems. Now, we are going to discuss a plane problem with uniform stress field using the Airy stress function. So here you see, let me first describe the problem. This is a plate. On this plate, these stresses are applied 2 times C2 here, 2 times C3 here, and these are the shear stresses that you are seeing, minus C1, this thing, and the shear stresses are applied, and this are applied throughout the plate. So all the stresses are applied in the plane. Okay. So, and this function has been given. This is a Airy stress function. So from where it came? It came basically for this kind of plate problems can be solved using this kind of Airy stress function. This one. So this is already available in the literature. From there it has been taken directly. These kind of functions can be developed using some kind of observations, because here you are solving the plane elasticity problem using heuristic approach, using the heuristic approach. So basically when you are using a heuristic approach, it means you are using some kind of observations, some kind of prior knowledge you are using. So this is already given to you. This can be thought of easily for these kind of situations. So suppose that the Airy stress function is a second order polynomial. So if you see, this is a second order polynomial. the lowest order that gives a non-zero stress field of the following form with zero body force field. So here we are using zero body force. There is no body force applied here. Only external stresses are applied. Body forces are not applied. So we want to see how Airy stress function can be used in this kind of problem. So let us start writing with the equation of equilibrium. So because this is a rectangular coordinate problem, so equation of equilibrium can be written like del sigma xx del x del sigma xy del y plus fx equal to 0 del sigma xy del x plus del sigma yy del y plus fy equal to 0. Now here you have to listen very carefully. When we use this Airy stress function approach, so Airy stress function is basically some kind of function. So that function is basically also known as potential. Okay. So for body force, we define a scalar potential. So that scalar potential is defined as Vf. And how it is defined? What is the definition of Vf? Definition of Vf is that if you differentiate this scalar potential with respect to x, you will get minus fx. And if you differentiate with respect to the y, you get minus fy. That's how body forces are defined in terms of scalar potential. It means that this scalar potential will be some function, scalar function of x and y. That's how you define the body forces when you solve using the Airy stress function approach. After that, so what was the initial definition of Airy stress function? The initial definition of Airy stress function was that Airy stress function is a kind of generalized function that will satisfy these equations of equilibrium. So to satisfy these equations of equilibrium, we need to define sigma xx, sigma xy, and sigma yy in terms of potential function phi. Fx and fy we have already defined in terms of Vf. Now we have to define, because this is same as sigma xy, so we need to define only 3 stress components in terms of phi. So we have to find a function phi such that, or at least we have to find the properties of phi such that this differential equation gets satisfied. So Airy stress function is nothing but we are trying to solve this kind of differential equation. It is as simple as that. Okay. So now let us define sigma xx as, so mathematicians observe that if you define del square phi del y square plus Vf, and if you define sigma yy as del square phi by del x square plus Vf, and if you define sigma xy as minus del square phi del x del y, if you use these kind of functions, then your 2 equations of equilibrium will be easily satisfied. Okay, how? Let us see. So first we need to calculate del sigma xx by del x. So if you differentiate this with respect to x, you will get what? Del 3 phi del y square del x plus del Vf by del x. Now this can be written as del 3 phi del y square del x minus fx, because del Vf by del x is equal to minus fx, that I have already defined. So let us define this as equation number 1, which is this. Second thing that you want to define, that you want to see, is del xy by del y, because that is the second term in the equation of equilibrium. So if you do that, you will get this del 3y phi del x del y square. This is your equation number 2. If you add 1 and 2, you get what? Del sigma xx by del x plus del sigma xy by del y. If you sum both the sides, so this term is getting cancelled with this term, and you are getting basically only minus fx on this side. So if you put all of them on the right hand side, you get what? Del sigma xx by del x plus del sigma xy by del y plus fx equal to 0. So this is your equation of first equation of equilibrium, which is easily satisfied if you put sigma xx like this, sigma yy like this, sigma xy like this. Now till now you have used only these two. This will be used when you will write the second equation of equilibrium. So similarly, using the same approach, second equilibrium equation can also be satisfied. Okay. So phi, which is phi, a function of x and y, this is known as Airy stress function. Now it can be shown, because we have also learned the compatibility conditions of strain. Okay, so from stress, and then you can assume some kind of deformation, and then strain, and then you can apply the compatibility conditions with lot of mathematics. It can be shown, finally it can be shown that grad 4 phi will become 0 if Vf is equal to 0, or body forces are equal to 0. So this is a very important relation. Am I audible, Govind?
Yes, sir, you are audible.
Okay, because
Yes, sir.
okay, thank you, because light has gone in my office, so I was thinking maybe I'm okay. So grad 4 phi equal to 0 is a very important relation. So basically, if you solve this differential equation, you will get the phi. So your Airy stress function will always satisfy this equation. So how to define grad 4? So grad 4 is nothing but 2 Laplacian of a Laplacian. So this is also known as biharmonic operator, and it is defined as del 4 del x4 2 times del 4 del x square del y square plus del 4 del y4. So this is your biharmonic operator, and Airy stress function will satisfy this equation if body forces are 0. Okay. So similarly, right now you have written for the rectangular coordinate. Similarly, you can also write for cylindrical system. For cylindrical system, your radial body force will be minus del Vf by del R. Your theta direction radial force will be minus 1 by R del F Vf by del theta, and sigma RR in the case of cylindrical system will be 1 by R del phi by del R plus 1 by R square del square phi by del theta square plus Vf. Just like we defined sigma xx in terms of phi, sigma theta theta can be written as del square phi del r square plus Vf, and sigma r theta equal to minus del by del r 1 by r del phi by del theta. So basically you can see yourself that if you put these in the equilibrium equations of cylindrical system, so these kind of functions will certainly satisfy the cylindrical equilibrium equations, just like I have shown for the rectangular system. Okay, so that can be shown with little bit of maths. So with this basic idea, now we again go back to the original problem that we started discussing here. So this was the problem. For this problem, this was the phi. Okay. So the objective is that we want to understand about that how this kind of problem can be written in the terms of this Airy stress function. So if you write here, so let me write grad 4 phi equal to 0 because body forces are 0. It means del 4 del x4 plus 2 times del 4 del x square del y square plus del 4 del y4. So now phi in this case is c1 xy plus c2 x square plus c3 y square. Let us check whether this kind of functional form is satisfying this equation or not. Let us check. So if you want to calculate grad for phi, so basically here it should be phi because you are putting this operator here. So let us calculate the first term one by one. This. What will be the value of this term? Rohit Kumar Verma.
Sir, 0.
Very good. What will be the value of this term?
All will be 0, 0, 0.
0. And this term will also be 0. So basically, this kind of function is satisfying this equation. So it means phi is a valid Airy stress function. Now, how can you write sigma xx? How to calculate sigma xx from the given phi? Vikram.
Yes.
How to get sigma xx from this phi? Rahul.
Sir, with sigma xx is equal to and del square phi by del y square.
Del square phi by,
Del y square
that's it,
plus
plus
Vf. What? Vf.
so body force is 0 in the present problem.
0.
So what will be the value of sigma x finally for the present problem? Tell me what will be the value of this
by C3.
2
2
what was
C3.
5? 2
5 equal to
C3. Very good.
C1x. Yes.
And sigma y by
Sigma 2. 2 C2.
Saurabh, sigma y by
2, sir.
eh?
2.
2, that's it.
2C2, sir.
2 C2. And sigma xy
Minus C1.
minus C1.
C1.
Okay, very good. So basically what it is showing, if you see, sigma xx is 2C3, sigma yy is 2C2, sigma xy is minus C1. Okay, note this down and you'll see here. Sigma xx is what? So this is your minus C1, the sigma xy. 2C2 is this one and 2C3 is this one, if you see very clearly. Okay. So these uniform stresses on this plate are basically coming from this kind of Airy stress function. So these values of 3 stresses you have calculated from this Airy stress function basically. So these two are linked. So these were not arbitrarily. These were coming from this kind of Airy stress function. And this Airy stress function satisfies the basic condition. And this basic condition is true only when your body forces are 0. Okay. So that was a small lecture, or you can say thing on Airy stress function. Let us say bye bye to this one. So we have covered Airy stress function. I will upload this thing also on your Moodle. Now we are going to start the next lecture, that is asymmetrical bending. So till now you have studied the cases of symmetrical bending of beams in a symmetrical way. But now we are going to start to study the asymmetrical bending of beams. So when we talk about asymmetrical bending, it means there will be some kind of twisting. So when you bend properly something, so it will bend properly, but if you are doing some kind of asymmetrical bending, of course there will be some kind of twisting in the system. Okay, so we want to study about that, the unsymmetrical bending, which is more practical case in real life. So first let us start with some very basics. The problem of beam bending and stretching has already been discussed. We have discussed the problem of beam bending and stretching in the previous lecture, in the when we were discussing elasticity. Correct? That has been already discussed. Now here, this is a simple prismatic beam or bar that you see here. This one, which is completely symmetrical. So we know that the basic assumption that we know that the sections that are plane before bending will remain plane even after the bending. And this is a simple symmetrical bending that you are seeing the case of. So we discussed about the Euler-Bernoulli beam. We discussed about the Euler-Bernoulli beam, the problems of the Euler-Bernoulli beam, and what are their assumptions. Okay. So if you remember, the basic equation of Euler-Bernoulli beam was, which you have already studied also, I am writing here. This is basically mz by iz equal to minus sigma x upon y equal to E by R. This is very popular equation. Each one of you might have seen somewhere. So here, if you see in this figure, this is mz, okay, the moment that has been applied. So Iz is the area moment of inertia about the neutral axis which passes through the centroid of the cross section. So this is basically centroid of the cross section and your neutral axis is passing through this. So we are calculating Iz about that. E is Young's modulus of the beam material, which is coming here. R is the radius of curvature of the bent beam. So when beam is deforming, it will have this kind of deformed shape. So this deformed shape of the beam will have some radius of curvature. So this is that. And a positive bending moment mz produces a compressive stress at a point with positive y coordinate. So usually the sign, this is just a sign convention. You can use your own sign convention also. So I'm not very strict about the sign conventions. So your sign convention is something that decides whether this will be minus sign or plus sign. So some of you might have seen this equation with plus sign. Some of you might have seen this equation with minus sign. That will depend what kind of sign convention you are using. Okay, so there is nothing so much, what should I say, complexity about that. Okay, that is just basic stuff about Euler Bernoulli beam. Now, in the case of asymmetrical bending, when the bending moment acts in the plane of symmetry, the beam is said to be under symmetrical bending. So here, if you see, the bending moment is acting in this plane. So basically this is a jet plane, this is going like this. So on this particular plane, the bending moment is acting and this plane is symmetrical. And this is the, you can say, the neutral axis that is passing through the centroid in this case, and moment is acting along this axis. This is completely a symmetrical case. So this is the case of symmetrical bending. If this is not being followed, for example, in the same case, suppose if you apply bending moment, suppose, let me clear this one, it is falling, okay. So suppose if you, instead of applying the bending moment along this axis, if you apply, say, the bending moment about this axis, so say this is some axis that is passing through the cross section and you want to apply bending moment along this axis. So this becomes asymmetrical bending. This will lead to some kind of twisting. If this is a offline class, I could have shown some example, but in online class, it may be a little difficult to show this thing. But this can be very easily shown in the offline class. But I hope you are understanding this, that I have taken this axis and I'm applying the bending moment along this axis. Then it becomes a case of unsymmetrical bending. Okay. So let us also see one simple case. So this is a cantilever beam. At the tip of the cantilever beam, if you see from the side view here, you will see this vertical force 1000 Newton is being applied at the tip of the cantilever beam. But if you see from this angle, you will see this. And here when you see this 1000 Newton, which was looking vertical from here, actually it is inclined at an angle 30 degree to the y-axis. So this will of course produce, so this is basically passing through your centroid. So this will have two components, one component like this and another component like this. So this will have bending, you can say, in the two, along the two axis. Okay, so basically this is an asymmetrical bending case and this may cause some kind of twisting of the system. So a cantilever beam of rectangular cross section is subjected to a load of 1 kilonewton, inclined at an angle of 30 degree to the vertical, like this. We want to determine the stress as point D. So what kind of problem we want to deal? So this location we want to determine the what stresses will come here in this case. Although this case may be solved very easily, but there is a detailed philosophy behind it. So we want to understand the detailed philosophy behind those kind of problems. So we will start with some basics of such problems. Okay, what are the basics of that particular problem? So first assumption is that the sections that are plane before bending remain plane after bending. This assumption will still be there. Okay, so this is Euler-Bernoulli hypothesis. This means that the cross section will rotate about an axis such that one part of the section will be subjected to tensile stress and the other part above that axis will be subjected to the compression. You know that. And points lying on this axis will not experience any stress because that is a neutral axis. Consequently, this axis is the neutral axis that you know. Okay. Here in this diagram, it is shown that line BB is neutral axis. Here, this is the neutral axis. So now the neutral axis will not be along the like this. So neutral axis will be like this because this is the case of asymmetrical bending, and it will pass through the centroid. However, this neutral axis will be inclined at an angle beta with the y-axis. If beta equal to 90 degree, then this will be the symmetrical bending case. So if this beta, the angle that you see here, if this is 90 degree, so this basically BB line will be passing like this. Okay. So this kind of neutral axis you have seen in the case of symmetrical bending. But in the case of unsymmetrical bending, the neutral axis will be something like this, and that will be passing, that will be tilted at an angle beta with respect to the y-axis. Now, this neutral axis BB will pass through the centroid, the geometrical centroid of the system. So we want to first prove that thing, that it will pass through. So for this, consider a small area lying at a distance y from BB. So how to prove that? Let's go step by step. So we have taken a small area, this, which is lying at a distance y prime from BB. This is 90 degree. So we have taken vertical distance. Since the cross section rotates about BB, BB is this. During bending, the stretch or contraction of any fiber will be proportional to the perpendicular distance from BB. This is the standard thing that you already know. Okay. So we can write here. So let me first introduce some blank sheets. Only then I can explain this one. New slide. Okay. So now here we will do a little bit of description. Asymmetrical bending. So we want to prove that BB will pass through the centroid. Okay. So strain in any fiber can be written as epsilon xx k prime y prime, where k prime is some constant, some proportionality constant, k prime y prime. So here you need to know that only sigma x is acting. Sigma y and sigma z are basically 0 because we are considering only pure bending case. Although it is unsymmetrical, but even in the unsymmetrical case, only stresses will be along the sigma x. The distribution will be unsymmetrical. That is another story. That's what we want to discuss here. But all the stresses will be only in the sigma x direction. That's what we are assuming here. So now sigma x can be written as modulus of elasticity into epsilon xx. Epsilon xx is what? K prime y prime. So we can also write E is constant, modulus of elasticity, K prime is also a constant, which is basically the proportionality constant, and we are multiplying by y prime. So y prime is basically this distance, if you see. This distance, y prime. We are calculating strain in this particular fiber. Okay. So epsilon xx here is K prime y prime, and sigma xx will be E k prime y prime. So E k prime we can write collectively as ky prime. So the force acting on this delta A, force acting on delta A. So sigma xx multiplied by delta A. So let us say delta fx. That can be written as k y prime delta A. That can be written. Now we know that equilibrium in x direction. So basically a resultant force in x direction can be written as integral of this force over entire area, cross section area, and that should be equal to 0 because this is in equilibrium. So you see that first moment of area is 0 about BB. So this is everything we have calculated about BB, because y prime is, this y prime is being measured from BB. If y prime is being measured from BB and you are getting this relation which is saying integral, area integral k y prime dA equal to 0. So k is a constant you can throw out. So this will become y prime dA equal to 0. If you see this thing carefully, this is nothing but first moment of area about BB, and this is equal to 0. It means this is the basic result that BB is passing through centroid, geometrical centroid of the section. This is the basic result. So BB is a centroidal axis. So this thing we have basically proved it also mathematically, that bending will happen about this BB axis, and BB is the neutral axis. Now second important thing. So first thing we have proved that it is passing through this point, the centroid. What is the second important thing if you want to determine BB? Anyone? What should be the second thing? So if there is a cross section, okay, let's say this is some random cross section. This is centroid of that cross section. First information, you know that neutral axis is passing through this particular point O. Okay, and this is your basically axis. So y axis and z axis. X axis is inside along the length of the beam. This is O. So basically, you know that neutral axis is passing through O. What second information is required to locate the neutral axis? This is just a small mathematical problem. You want to find a line, you know the one point of the line, one point on the line. What second thing you want to have? Anyone? Hello? Govind?
Yes, sir, you are audible, sir.
Oh, we are not audible. Okay.
Distance, sir.
Distance from where?
From that point to where I want second point, sir.
No. So basically, you know one information that your neutral axis will pass through O. So neutral axis can be basically any. There can be infinite lines which will pass through O. Okay. Say one line is this. One line is this. One line can be this. Like this, there will be infinitely many lines. But which of them is going to be the neutral axis? So you need one more information, right?
Sir,
What?
angle is 90 degrees. Angle.
Very good. So it is not 90 degrees, but you are very close. There is an angle involved. So which angle? I have shown in the previous slide.
Sir, the force acting.
This angle here. This angle beta. If you know that your neutral axis makes angle beta with your y-axis, so there are several axes. This, there can be infinitely many axes. But another information that you know that your neutral axis makes an angle beta with the y-axis. If you know that, then you have the information about the neutral axis. So this becomes your basically neutral axis. So B, this becomes your neutral axis. So neutral axis, you need to have two information. First information is that it passes through the centroid, that we have already proved. Now we want to calculate beta. If we know the beta, value of beta, we can very easily determine the actual location of your neutral axis. So beta will be 90 degree in case of symmetrical bending, correct? That we already know. But here beta will not be 90 degree. It can be something, okay? But it will not be 90 degree in case of asymmetrical bending. So basically we want to identify this value of beta. Okay. So in asymmetrical bending, the beam will not bend in the plane of the bending moment. So that I have already discussed. And the neutral axis BB will not be along the applied moment. So now we are interested in determining this angle beta. So let us try to determine the angle beta. That is our next target. So let me bring this thing here. So you have any other class after this right now?
No, sir.
So I can continue, right? Some basics. Principal is my here. Okay. So I was here. So now our target is that we want to determine the angle beta. Okay. So there are few interesting observations which are required to determine the angle of angle beta. The first observation is that there is no movement about y-axis. There is no movement about y-axis. So this is y-axis. No movement is acting about it. Okay. So basically, if you take the moment about this axis, this will give what? Sigma x into a, sorry, dA, that is the force. So let me erase this one. Sigma x is the stress acting in the x direction, dA, and into z equal to 0. So basically for this particular point, if you see, so this is basically z, distance from the y-axis. So that you are multiplying here. So on this small area dA, the force stress is acting sigma x. So sigma x into dA is the differential force. If you multiply by z, you get the moment about y, and if you integrate on this entire area, you get this equal to 0. Now you know that sigma x is basically, we have already calculated that it will be k y prime z dA equal to 0. So this will be your first equation from your first observation. Second observation is the moment about z axis is, in this case we have chosen z axis such that your movement is acting about the z axis. So here you see the moment about z axis is mz. So how will you write the equation from this observation? Similarly to this, you have to write Rahul. राहुल आज है नहीं क्या क्लास में?
Yes, sir.
Rahul, tell me from the second observation that your movement is acting only about z axis. How will you write the movement equation? Just like this you have to write. It is very simple. Tell me. राहुल,
Yes, sir.
बताइए. Force कितना? So let us take this element. Okay, let us take this element. So on this element, what is the distance of this element? Let's say y. Okay, let's say y is the distance, this y. Okay, so for this y, what is the moment from this element, coming from this element? Okay, what is stress acting on this element? Can anyone tell me what stress is acting on this element?
Sigma x.
Very good, very good. So what force is acting?
Into DA.
Into dA. Very good, very good. Now you know the force. Now what is the moment about z axis?
Into perpendicular distance, sir. Y.
What is perpendicular distance?
Y, sir.
Y. Very good. Now you want to add all the such elements about entire this area. So how will you add?
Integrating.
Integration. Very good, excellent. So integration, so if you integrate this term on the entire this cross section, what you will get?
MZ.
Eh?
MZ.
Mz. Very good. So this was the simple equation, that movement equation. Okay, so this was not something difficult, but anyways, so sigma x y dA equal to mz. Now if you put sigma x again as, what you want to put sigma x? Ky prime, ky prime into y into dA equal to mz. So this is your second equation. First equation was this. First equation was what? K y prime z dA equal to 0. This was your equation number 1. Equation number 2 is k y prime y dA equal to mz. Okay. So from this equation, k is a constant, you can remove. So you can write integral y prime z dA equal to 0. And from this equation, if you take k constant, that is outside, y prime y dA equal to mz. Okay. Now, if you see here, the y, so this is nothing but replica of this thing here. This is your neutral axis BB, which is making an angle beta with y-axis. This is your z-axis about which your moment mz is acting. Okay, and then here this is y prime, distance of this particular element here. This is y prime. Okay, so now here you can very easily write y prime as CF minus DF. CF minus DF. CF minus DF. That is your y prime. So DF is what? If you see this DF, so DF is nothing but z cos beta. So you know the DF, and CF is basically CF. You can write in terms of y as, so this entire length can be written as y sine beta. If you put that here, you get y prime as y sine beta minus z cos beta. Now let us substitute this one here. So we got this equation, y prime z dA equal to 0. If you substitute here the value of y prime, you get what? Y sine beta minus z cos beta into z dA equal to 0. Let us write it further. Integral y sine beta z dA minus integral cos beta z square dA equal to 0. I have done nothing, just multiplied and separated the integral. So you know that beta is constant, it is not changing with the area. So you can take this out. So sine beta times area integral of y z dA minus cos beta in bracket area integral z square dA. This becomes equal to 0. So in double integral y z dA, what is this? Okay, let's start with simple one. Z square dA. What is this?
Moment of inertia.
Moment of inertia. Excellent. About
Centroidal axis.
which axis? There are two centroidal axes, y axis, z axis. This is central. This is moment of inertia about which axis?
Y.
Which?
Y-axis.
Y-axis. Very good. Excellent. So this is moment of inertia about y-axis, and this term is basically written as basically product of inertia about yz, Iyz. Okay. So using this, you can write like Iyz sine beta minus Iy cos beta equal to 0. From here you get what? Tan beta equal to Iy upon Iyz. This becomes your, so from this equation you can easily identify beta. Now neutral axis can be determined easily because we know beta and we know that it passes through the centroidal axis. So we know both the things. So now we can very easily identify the neutral axis. Here you have to notice that while deriving this angle beta, one assumption was made that your moment is acting about z-axis. This is very important assumption because only then you can write my equal to 0. So this was equal to 0 because there was no movement acting about y-axis, and when you wrote mz, equation for mz, that was possible because your movement was acting about z-axis. Okay, so I will stop here. And so till now we have determined the angle beta, and we know that this centroidal axis will pass through the centroid, and we also know that beta equal to 90 degree if it is a case of symmetrical bending. If it is not a case of symmetrical bending, then beta will not be 90 degrees. These are the takeaway message from this particular lecture. So after that, now I will, oh, where I have gone? Sorry. Okay. Now we will discuss in the next lecture principal axes OZ prime and OY prime, and we will discuss what are those and how we can move ahead from there. Okay. So all the best for your midsem, and I will inform you about the midsem. All the best. And today also there is a deadline for submission of your first project report. Okay. So I will stop recording.